In this lecture, we're going to review some calculus with topics specifically related to economics. We're going to begin with elasticity, which is defined as the percentage change in the dependent variable due to a percentage change in the independent variable. Therefore, it has no dimensions. And by a percent change, we mean the change in some variable divided by its level. So let's suppose that Q is a function of P. So quantity is a function of price, in which case we either have a demand or a supply function. We're not interested in which is which at this point. And we define the elasticity associated with that particular function as the limit as the change in the price approaches zero of this function here, the delta Q, the change in Q over Q. So this is our percentage change in Q, and we divide that by the percentage change in price, which is delta P over P. Now, part here can be rewritten as this, as P over Q times delta Q over delta P. And you should immediately recognize that this delta Q over delta P is a slope, all right? But in this case, Q is on the the horizontal axis, pardon me. P is on the vertical axis. So what you've basically got is 1 over the slope of the supply or the demand curve. So we're going to take the limit as the price goes to 0, and we get this particular expression here, P over Q times dQ over dP. Or we can rewrite this as P over Q times 1 over the slope of either the supply or the demand function, depending on which is which. Now we define elastic as elasticity which is greater than 1, and we notice that it's in absolute bracket. So in other words, it's the absolute value. So for example, in a demand function, we have a negative slope. So as a result, we would take the absolute value of that in order for it to be elastic. If the elasticity, the absolute value of the elasticity is less than 1, it's inelastic. So let's look at an example. For example, in this case, we're going to show that a monopolist would not produce in the inelastic portion of a linear demand function. So here we have our demand function, which we describe using this equation here, where this is the demand price is equal to some A minus BQ. A is the intercept here on this axis at 0.3, and B, or minus B rather, is the slope of the demand curve here. Now we construct a marginal revenue curve simply by dividing that slope by half, which means that we're multiplying 2 times B. And then this is the expression for the marginal revenue curve. Why do we multiply by 2? Because that means it's going down faster than the demand function is going down. So we look at these 3 points. At point A1 here, we know that A minus BQ, so the price, this price of demand, or if it's, it's a demand function, is equal to A minus BQ, but we know that this price is 0 at this point, so we have A minus BQ. Q is equal to A over B, which is this point here. The elasticity then is 0 because that P is equal to 0. At point 2, we have A minus 2BQ equals 0. Q is equal to A over 2B now, and the price we can determine, which we want to find here, this will be the accompanying price, would be A minus B times Q, where Q is A over 2B, and the price is then A over 2. So let's look first at point 4. And we have that the elasticity is P over Q times 1 over the slope. The slope here is minus B. All right, remember this expression was dq over dp, and we want dp over dq, which is this. This value here is the value of the price. This is our q, which we determined to be here a over 2b from 0.2. And when we plug these in, you see immediately that these two cancel, and with this b brought up, we get a -1 being the elasticity. At 0.3, at this intercept, q is equal to 0, and we find that when we carry this out, we got a 0 here, we've got a minus b. So what this does is it means we have a minus infinity because of that negative and because of that 0 there. Since the marginal cost will intersect marginal revenue to the left of 2, all right, so it's going to intersect someplace here because marginal cost is not going to be negative. It's always going to intersect that marginal revenue curve somewhere to the left of 2. The monopolist will always operate in the elastic portion of the demand function. So the demand function between 0 and -1 is less than in absolute value than 1, and so it's inelastic in this range, and it's elastic in this range. So the monopolist will always operate in the elastic portion of the demand function. Now we can look at some further proof by looking at total revenue, which is equal to P as a function of Q times Q. Remember, if we're dealing with a monopolist, that means that the monopolist has some control over price, which is why we write price as a function of Q. Taking the derivative of the total revenue equation with respect to Q gives us the marginal revenue, and we get dP dQ times Q plus the derivative of Q with respect to Q, which is 1 times this term here, which gives us that price. And we rearrange that. We take the price out, and we get 1. We've just reorganized this, so this is our 1 here, times dP dQ times Q over P. So we divide this by P in order to be able to take that P out. And this, you'll see, is the expression for the elasticity of demand, but it's 1 over, because remember, the elasticity of demand is P divided by Q times dQ dP. So as a result, the marginal revenue is equal to the price times 1 plus 1 over the elasticity of demand. Now, when is the marginal revenue going to be positive? Well, that's if this expression is positive, because the P will always be positive. So rearranging that, we find that the elasticity of demand has to be less than -1. Where is it less than -1? Well, it's less than -1 from this 0.4 down to this 0.3, where it's negative infinity, and any number like a -2 or something will be less than -1. So let's pick -2. So if the elasticity of demand is -2, we then get 1 plus 1 over -2 equals 1/2, which is greater than 0. So the marginal revenue will be greater than 0. For demand functions, then, the elasticity of demand less than -1 implies total revenue is going to go up when the price goes down or the quantity goes up. Marginal revenue is less than 0 when the elasticity of demand is between 0 and -1, as shown here. So total revenue will go down when Q goes up. So based on these two results, all right, we end up that the optimal will be where marginal revenue equals marginal cost. Now, let's look at the elasticity of supply for a linear supply function that goes through the origin. And I'm going to let you, as a student, try and figure that one out. You should prove to yourself that any supply function, any linear supply function that passes through the origin is always going to have an elasticity of 1.0. So let's look at optimizing single variable functions. All right, here we've got some polynomial function that bottoms out at A and at C, and it's at a maximum point at B and again at D. So in other words, if we find the first derivatives of the function and set them equal to 0, so if we take that function, find the first derivative, set it equal to 0, we'll end up, if this is the function that somehow it's constrained to be in this diagram, then we will find 4 points where the first derivative of the function is equal to 0. Now notice that there are 2 minimum points, 2 minima, A and C, and 2 maxima, B and D, and that there's a global maximum at D. Now the problem, of course, is that even with second order derivatives, we will have a hard time determining whether D is the maximum or whether B is the maximum. So you sometimes end up, if you're doing a computer program where you're solving functions numerically to try and find the maximum and minimums, they'll get caught in these are all local maxima or minima, and you need to somehow explore the function over a larger range, like the whole range of the function, in order to determine which is going to be your global maximum and which is going to be your global minimum. The global minimum looks to be A, but it could be C as well. However, a necessary condition for a maximum or a minimum is simply that you set that first derivative, dy dx, which we denote f prime of x, equal to 0, if f prime of any particular value x0 is 0, and if the second derivative of that function at x0 is less than 0, then fx has a relative maximum at x equals x0, and the function is concave in that particular region. So in these two regions, it'll be concave. Now, if you find one of these points, A, B, C, D, call it x0, if the first derivative of the function at that point, x0, is 0, and if the second derivative is greater than 0, then f of x has a relative minimum at x equals x0, and you get a concave function. So the function is concave in this region, and this region, it's a convex function in this region, and a concave function in those two regions. So a convex function has the property that f prime of x0 is 0, and the second derivative, f double prime of x0, is positive. So you have to remember that, and we'll get back into that in a little more detail later on. Consider an example of y equals x cubed. And when we take the first derivative, set it equal to 0, we find that x0 is 0. Take the second derivative, and x is 0, so the second derivative is 0 at x0. So what we have here is an inflection point, okay? So compared to the other examples, we do not have a particular maximum or minimum, we simply have an inflection point. So if that second derivative tends to be 0, then we have inflection point and not a hill or a valley. As another example, consider that profit is total revenue minus total cost. We write that as revenue RQ minus CQ. Take the first derivative of pi with respect to Q, and we get that the first derivative of the first derivative of R with respect to Q minus first derivative of C with respect to Q, R prime Q minus C prime Q equals 0. Setting those equal to each other, we get R prime equals C prime, or more generally, because R prime is your marginal revenue and C prime is your marginal cost, that marginal revenue equals marginal cost. Now, if we look at perfect competition, the big difference there is that with perfect competition, we don't have price as a function of Q. Rather, it's considered to be a scalar that's determined in the market, and the producer has no control over that particular price. So in perfect competition, we write total revenue is price times Q, and we take the first derivative of that, so we get R prime Q equal to P as opposed to marginal revenue. So marginal revenue here is equal to price in perfect competition. So therefore, we get that P is equal to your marginal cost. So above we showed that for monopoly, R prime Q is P times 1 plus 1 over the elasticity of demand. Thus, for monopolist, we have that P times 1 plus 1 over elasticity of demand equal to the marginal cost. And we're interested in the second order condition for a maximum profit. So we take the second derivative of the profit function, which was way up here. Here's the profit function again. And what we're going to do is we're going to take the second derivative of it. And for a maximum, it has to be less than 0. So again, we take the second derivative of the revenue function and of the cost function, subtract the second derivative of the cost function from the second derivative of the revenue function, and we get first derivative of the marginal revenue function minus the first derivative of the marginal cost function. And it has to be less than 0. This is the slope of marginal revenue. It's the first derivative of the marginal revenue with respect to Q. So this is the slope of the marginal revenue function, and this is the slope of the marginal cost function. So basically, if we rearrange that, we get MR prime is less than MC prime. So the slope of the marginal revenue function must be less than the slope of the marginal cost function at the optimum. All right, at the place where marginal revenue equals marginal cost. Now, this is met in the usual case because the marginal cost function slopes up, so that's a positive, and the marginal revenue function slopes down, which means it's a negative slope, and a positive is, of course, greater than a negative. So, in other words, slope of marginal revenue is a negative, slope of marginal cost is a positive, so the negative is less than the positive. So this particular condition is met. However, there are cases where marginal cost and marginal revenue are both rising, or perhaps marginal cost is falling and marginal revenue is falling. I don't think that's right. Marginal revenue does not rise, it simply falls. So sometimes the marginal cost is falling as well, and then it becomes a little more difficult to determine whether this condition holds. Now suppose that total cost is 100 minus 2q plus 5q squared, then the marginal cost is 10q minus 2. The average cost is given by the total cost divided by quantity, so it's 100 over q, 2 over q divided by q is minus 2, and 5q squared divided by q is 5q. What is the fixed cost here? Well, it's clear that it's 100, so that's your fixed cost. So we can graph that particular situation by looking at and calculating what the total cost is at 0. We said it's 100. Marginal cost, the average cost doesn't exist at that point, and we know the marginal cost also is minus 2. And we can calculate these numbers right up to 10, and you see that the average cost curve falls, and then at 43, at quantities of about 4 or 5, it flattens out, and it begins to rise. The marginal cost curve rises throughout. And we've plotted this. I've just plotted this very roughly. You see that at 1, Q1 is 103, that's approximately there. At 2, this is the 103 on there. It's 58, which is about here, and so on, and we can just plot that average cost curve, and it hits around 4 or 5 and then begins to rise. The marginal cost curve rises throughout, and this point right here is then the point where the average cost curve reaches its bottom, and it's intersected from below by the marginal cost curve. So can we prove that? Well, let AQ represent average cost and MQ the marginal cost. So total cost is simply the quantity times the average cost, all right? And that's taken from here, okay? Total cost is, move that over, and you get average cost times Q. The marginal cost is the total derivative of the total cost with respect to dQ, which, when we do that, is Q times the derivative of this plus AQ times derivative of Q with respect to Q, and we get Q A prime Q plus AQ, because that Q just drops out for this particular second term. The average cost, this AQ, reaches its minimum point at the first derivative of the average cost function. The marginal cost curve can be written as Q times 0. All right, the 0, of course, comes from the fact that A prime Q is 0 at its minimum plus AQ, so that means that the marginal cost is equal to the average cost at the minimum of the average cost. Now, take the first derivative of average cost, and we get 1 over Q times, in square brackets, marginal cost at Q minus the average cost is at Q, which is from this result up here, all right, this equation here. So we take the second derivative, and we get Q times M prime. So the slope of the marginal cost curve minus the slope of the average cost curve, both at Q, minus the marginal cost minus the average cost divided by Q squared. All right, so that's if we rearranged this marginal cost that we're looking at. So we're taking the derivative of that. At the minimum, A prime Q equals 0, and it turns out, as we've shown, that the marginal cost is equal to the average cost. And the question is average cost rising, or is that really a minimum? And this is the condition for a minimum. So we take the second derivative of the average cost, which is equal to the marginal cost. The first derivative of second derivative of the average cost rather is simply marginal over the slope of the marginal cost divided by Q, and it's greater than or equal to 0 since top, this part here, which is equal to this, is greater than or equal to 0, and Q has to be. So let's assume it's falling average cost. So then the first derivative of average cost is less than 0, and then 1 over Q, MQ minus AQ, so the marginal cost minus the average cost, is less than 0, which implies that average cost is greater than marginal cost, which in turn implies that marginal cost intersects average cost from below. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.